we have some very nice stuff to cover today. Uh, Today is the last class we uh, started discussing context-free grammars, right? So CFGs, we saw examples, more powerful than DFAs, right? And I told you that they're important for programming languages, for instance, okay? Today, my goal is to, we'll basically explore some more properties of CFGs and how they kind of where they rest in the full spectrum of computational models. All right. So today, more examples, CFGs, kind of closure properties, maybe, and computing, semantic properties of CFGs. Okay, so that's our target for today. And let's see exactly where we were last time. Okay, so we designed this language for addition last time, right? And then I ended up with the statement that double is not context-free. So we'll work towards that. But before that, let me do a couple of other things which will set the stage nicely for the closure properties and how it'll tie into proving languages are not context-free. Okay? And as I said, if you're playing around designing context-free grammars, there are some simple sort of heuristics you can keep. Just like for DFAs, you have to play around, develop your intuition by working with some examples. Some heuristics are kind of like to break up the language into cases. Okay, so we'll do one of those. And trying to use that, DFAs are context-free. Trying to use a union of two context-free languages is also context-free, and so on. Okay. All right, so let me give you one more example. We already saw that if I set L to be 0 to the n, 1 to the n, this was context-free, right? So we saw a simple grammar for this. Okay. Now I want to do something slightly different, which is 2 to the n. Okay, my claim is that now my terminals or alphabet has three things, 0, 1, comma 2. And my claim is that this is context-free. Let me call it L1. Can you give me a grammar which generates exactly this particular language or these kinds of strings? Any suggestions? So we already saw how to do, so let me remind you. So we saw this. Right? So if we had this generated 0 to the n, 1 to the n is greater than or equal to 0. Okay. Now I'm adding one twist, which is I have a new sort of thing at the end, like an appending, which is 2 to the m. My claim is that this is now, the new one is also context-free. So how can I get a grammar for this? In particular, how is there a way to modify this so as to get L1? Any suggestions? Any guesses? So remember we talked about concatenating too, like how concatenation is somewhat easy with context-free grammars. Any sessions? So we already know how to get 0 to the n, 1 to the n, but now there's something, you also need to get some 2's in the end, right? So how can I generate those kinds of strings? Yeah. Right. So I'm just going to modify this to say something like s goes to 0, s1. Okay, so let me do it this way. That's it, right? So, this part is just generating the same thing, 0 to the n, 1 to the n. Okay. And now I have S2, which is basically going to generate as many 2's as you want, right? Particularly, this is how we argue that if I concatenate two languages, it'll still be a context-free grammar, right? Okay. That's one. Now, let me do a variant of this. Hopefully it'll become clearer later on why I'm doing these specific examples. I think there's a nice conceptual takeaway that'll show up later on. Okay. So now I want to generate strings which are similar form, a bunch of zeros followed by ones followed by twos, but now the number of ones and twos is exactly the same. Right? Earlier we had the same number of zeros and ones and twos were arbitrary. Now the number of zeros and number of ones and twos is the same, but the number of zeros is arbitrary. Okay. Can you tell me a grammar which can generate this? Any sessions? Yeah. Exactly, right? So, we don't have to start from scratch. We kind of know what to do. We just need to interchange what the roles of these things are, right? So maybe let me make this S1. Right? So now I'm making sure that every time I generate a 1, I also generate a 2. So the same number of 1s are being generated as the same number of 2s. And the number of zeros is completely independent of it. Okay? Good. We have two other languages which are context-free. Let's keep that in mind. Okay? And I want to do one more example, which is the following. This one's a bit trickier, but I think it's worth doing it. Okay. So recall, we had this language double, which was WW, W belongs to 0, 1 star. Right? So double was the set of all strings where the first half equal the second half. Okay? And now this new language I'm defining is basically the complement of double. Things which cannot be written as two things, repeated. Okay, so the string repeated twice. Does that make sense? Does the definition of the new language make sense? It's just a complement of double. I'm just calling it L for now. Okay. So, that is L is the complement of double. Okay. And my claim is that, and this is a bit tricky, so we'll work towards it a little bit slowly. And then hopefully it'll be clear why, what do we learn from these examples? There is a message behind it, so let's work through this first. Claim double complement is context free. Okay, meaning there is a grammar which can generate exactly those strings which cannot be written as string repeated twice. All right. Any questions? Okay. So how do we prove such a thing? How can I generate all possible strings in the complement of double? Any suggestions? Well, maybe let's take it one step at a time. I want to claim that there is one big class of strings in this particular L, which are very easy to describe. And what is that class of strings? Any guesses? There's one big class of strings there which are easy to certify they are of this form, that they cannot be broken up as repetition of the same thing. Single character strings, but there are only two of them. But there should be lots of other things which fit kind of the same mold, I would say. Yeah? Odd number, right? If a string has odd number of characters, then you cannot write it as a duplicate of a string, right? Because everything of the form WW has an even length. If this has 10, the next one also has 10, so you get an even number. Okay? So this double complement definitely has all odd length strings. So let's first generate them. Okay? So let's say odd equals all x such that x has an odd length. So this is an excellent observation that, clearly odd is in double complement. So how can we generate these? Yeah?
But not all things that are in double complement.
Yeah, for sure. Right. So we're just trying to see, okay, can I at least generate, we need to generate the whole thing. So I'm taking, as I said, it's good to find pieces that you can generate. The good thing with CFGs is then you can work with other things. Yeah. It's okay if there are many ways of generating the same string, that's totally fine. Okay. So let's see if we can get odd first. Any suggestions? How can I get odd length strings? Or okay, so suppose I just told you, okay, prove to me that odd is context free. What would you say? Yeah.
Like two terminals and or two variables, and you generate like one character string first, and then like succession of like two character strings.
Okay. I think that works. Yeah. So, okay, so let's see. I think this is what you mean. So A to B, let's say B goes to 0 or 1. Okay. And A goes to 0, 0, A, 0, 1, A, 1, 0, A, 1, 1, A, and maybe epsilon. Right? This is what you had. This is excellent. This works. Okay. I would have cheated. As I said, being a computer scientist, you always solve the misdirection, right? So I would have said odd is regular, so it's also context free, but this is better. Okay. So this is a grammar which generates this. Because you're basically saying I'm going to have one thing which is 0 or 1, right? And A is basically generating every even length string. Every time I generate a pair, and eventually disappear. Okay. There are lots of other ways of doing it. For example, again, exercise, check that this also works. Okay, this also works. What I'm doing here is, every time again I'm generating a pair, and then 0 or 1. It's just the same thing written slightly differently. All of these things work. Okay, so at least we have a big chunk of double complement now in our grip. Okay, but it's not all of double complement, as was pointed out already. So we need to figure out how to generate the remaining things. Okay, so we need to figure out how to generate even length strings X okay. If it's even length, then there's the first half and the second half, both are equal length, where we want to make sure that the first half is not equal to the second half, right? Because that's exactly what double complement is. Even length strings that cannot be written as WW. Okay, so we need to make sure that X first half and this is X second half. We need to make sure that these two are not equal. Okay, so how can I generate that? Any suggestions? This is a bit tricky, but let's play around and see if we can arrive at some things, some ideas which will get us there. Yeah.
Take your starting variable and split it into two variables, and then I'm not sure how you do it, but you'd make it so these two can never like equal to the same thing.
Right. So that's a good idea. The problem with context-free grammars, in fact, that's one of their limitations, and also helps us in some other aspects, is once I generate these two things, we have no control on how they evolve. Right. So once I get A, let's say I do S to AB, I can never tie what rules I apply to A to what rules to apply to B. Okay. So we want to do something like that, but we want to be a little bit careful. So how can I, make sure that the first half and the second half are somehow different? Any ideas? Okay. Well, let's think about what it means for these things to be different, right? So if they're different, then there is some position where they are different. This is a 1, this is a 0, or vice versa, right? So for example, there should be some position, right, where maybe this is a 1, this is a 0, or this is a 0, this is a 1. Okay, we should have something like this. Okay. So my suggestion is to focus on this. All right. Any ideas based on this? Okay. Well, let me give you another hint. So let's play around with this. We're just going to okay, so let's say this is what we are targeting. The 0, 1 case will just swap maybe. That's not a big deal. If you can generate these things, again, going to 0, 1 will also be similar. Okay. So what's happening here is I want to say that if I go some I positions in the first half, I get a 1. If I go some I positions in the second half, I get a 0. And that's what I want, right? But as was, the problem, this was kind of what you were suggesting. But once I split, it's very difficult for me to synchronize the ith position on the first one and the ith position on the second one, because the number of times I apply a rule, there is no constraint on them, right? So how do I do this in a paired way? Well, okay, so let's say this is I. The total length is even, right? So let's say each piece is of length m. Okay. So the first half is length m, the second half has length m, and uh, you know, this is in the wrong place. We want something like this. Okay. So it's difficult for me to pair them from the middle because I cannot control it. But what I can control is kind of how many steps I move in. Okay. So this is, what I'm going to try and do. So how many positions do I have here? This is m minus I minus 1. Okay. Again, forget the border cases for now. That is totally fine. And if I move I paces here, what happens? You copy a diagram. I think if I draw one picture, everything will become much clearer. Whoa. Okay, this is I positions. I'm going to, for whatever reason, with some intuition, think of I bits here. Okay. So I'm saying the one appeared I positions from here, and I'm going to think of I positions afterward. What's the length of what is left? Any guesses? My claim is that if I move it this way, then this particular 0 is actually exactly in the middle here. Right? So let's check that. So we had m and m. So I moved I. So my claim is that this would be m minus I minus 1, m minus I minus 1. Okay. I know, this is a bit of a leap for why you would consider this, but once you see it, we can check. My things are not to scale. Maybe I should correct that. That's better. Okay. So what does this look like? So there is one piece of the string where 1 is exactly in the middle, right? Followed by another piece where 0 is exactly in the middle. Does it make sense? Any such string cannot be written as w comma w. Okay, that's what this picture is showing. If there is a 1 and a 0, which is, 1 is exactly I positions from the beginning, and the 0 is exactly I positions from the middle, and the total length is even, then it has this structure. Okay, we can check the arithmetic. This is I positions, I plus 1, 2I plus 1. 1 I cancels out, 1, 1, 1, 1 cancels out, and then I have I plus 1, I plus 1, so the total length matches up. Okay, any questions about this? Right? I'm saying if there is a 1 and 0, which is kind of distinguishing, then I can think of it as two strings put together, where the first one has 1 exactly in the middle, and the second one has 0 exactly in the middle. All right? Okay. So now, with this picture in mind, how can I generate such strings? Any suggestions? Okay, so let's see. So idea generate strings where 1 is exactly in the middle. Concatenated with strings where 0 is exactly in the middle. Okay, so that's the template that we arrived at, right? And how can I do these two things? Again, concatenation is something easy for context-free grammar, so we can work on each half separately, right? So how can I generate strings where the middle symbol is a 1? So what's a grammar which can generate these strings? Any suggestions? No? Yes? Exactly, right? So in fact, the answer was kind of here. We just need to change this a little bit. I'm just going to erase this guy. Right? So what does this do? The middle one is always S until I substitute it with a 1. Okay? So that's for my things. I'm just going to make it S1 so that I don't get confused. And for the second half, what should I do? The same thing, but replace the 1 with a 2. Sorry, with a 0. Okay, and then just to avoid confusion, I'm going to put 2's everywhere. Okay. All right. And the only thing left to do is to put these two things together. So I can say S goes to my final grammar for okay is I'm going to say, okay, where was our odd thingy? Okay, so let's say this is S odd. So I'm going to say S goes to S odd, S even, right? And S odd goes to whatever we had here. Okay. And then S even goes to S1, S2, or to S2, S1, right? Because the first half could have a 1 or a 0 or 0 or 1. They could differ in either way. So this kind of captures that. And then I have the same rules. So S1 goes to you can potentially save variables, rules, etc. But we are not too worried about that, so that's okay. Okay, So the way it looks quite, the set of rules that we ended up with is complicated, but we came about to them by breaking it up into pieces. The odd things, we had a separate grammar. For the even things, we had two cases where the first half had like a 1 in one position, 0, and then they flipped 0 versus 1. And for 1 and 0, that's where we kind of figured out this trick that it's like 1 is in the exact middle of a string, followed by 0 is in the exact middle of a string. Okay. Any questions about this construction? Yeah. Oh, sorry. That's a good point. That should not be concatenation. That should be this guy. Right. It's a union. It's not concatenation. Yes. Thanks. Okay. Any other any other questions? Again, as I said, you can probably, save some stuff, work around it, save some equations, variables, etc. But this works. So that's fine. Okay. No questions. All good. The sort of big, maybe step or cleverness was in realizing this, right? So if it cannot be written as the same string duplicated, then I can write it as like concatenation of two pieces, where the first piece, the middle one is 1, the second piece, the middle one is 0, or vice versa. Okay, so that was a clever thing that we had to do. Kind of a rabbit out of the hat, but that works, right? Okay, so why are we doing all of this? So what did we learn? We just kind of, painfully, or not maybe painfully, but playfully, let's say, saw that three particular languages are context free. So this one was L1, which is 0 to the n, 1 to the n, 2 to the m. Okay, good. So these are all context free. Okay, meaning they can be generated by context free rules. Okay, now let me ask you a question. What is L1 intersection L2? I have two languages. What strings sit in both of them? One, they're all the same, right? I mean, this is a property of equality, right? Basically, the number of zeros is the same as the number of ones. The number of ones is the same as the number of twos. All three should be the same. Okay? And here's the punchline. In the next, remainder of the class today, we will show two things. One, this language, 0 to the n, 1 to the n, 2 to the n, is not context free. Okay? There is no context free grammar. There is no set of rules that you can put which will generate these strings. This is surprising, right? So far, everything we saw was kind of nice in terms of intersection and union, right? So DFAs, if two languages were regular, their intersection is regular. right? So if it was doable by NFS, also it's true. If it's doable by regex, also it's true. Turing machines, of course, they're closed in all kinds of things. It's also true, right? But now for context-free grammars, we have an example of two languages where each one of them is context-free, but their intersection is not context-free. Okay, so that's kind of a bizarre thing, but this is true for context-free grammar. Somehow we gained some power by going to context-free grammars. They're more powerful than DFAs, but they're not as nice, right? They're not closed under this intersection, which is a very basic property that you can think of. Okay, so for example, maybe someone says, okay, here's a program. Does it compile both in Python and some other language which looks like Python? Maybe, maybe not. You cannot generate it by context-free grammar. Okay, so that's the sort of besides the specific example, the moral is CFGs are not necessarily closed under intersections. Okay, they're closed under unions easily, but they're not closed under intersections. Okay, and in the same way, we'll also show a theorem that double is not context free. Okay, another surprising fail in terms of closure properties, right? So I have a language double bar, which is context free, right? The complement of double, but its complement is double, which is not context free. Okay, so again, the same thing we had for DFAs. If something was regular, if it was computable by a DFA, the negation of it is also computable by a DFA. For NFS, it was not immediate, but we had this nice approach. You had to go through DFS and so on, but eventually it was true. For Turing machines, of course, again, it's true. But for context-free grammars, taking a knot can take you out of the model. Okay? So that's the other moral. CFGs are not closed under negations. There are functions which are computable by context-free grammars, but their negation is not computable by a context-free grammar. Okay? Any questions about these takeaways and why this might be true? We have to still show these two theorems, but barring that, we have this sort of very clear message about context-free grammars. Okay, that was the reason why I wanted to do these examples in particular. Okay, and you can also really, if you want to dig in, you can check that the 0 to the n, 1 to the n, 2 to the n, its complement is still context-free. It's only this one that's not context-free. That also turns out to be true. You have to write down like maybe 10, 20 cases and prove it, but yeah, let's not do that. Okay, all right. But we still have these two surprising things. Why are or seemingly surprising statements? Why are these two things not context-free? Especially when we know that their complements are context-free, and each one, like first one at least, should be surprising, right? I can generate two languages, but the intersection is not context-free. Okay. All right. So how do we prove or get a handle on the limits of context-free grammars? And it turns out we can kind of do it by an approach very similar to DFAs. Okay? So unlike DFAs, we don't have this beautiful MNT style characterization really of how many nodes you would need and things like that. But there is an analog which is called the pumping lemma, which is pumping lemma for CFGs, which can be used to show limitations of context-free grammars. Okay, and its structure and everything is very similar to pumping lemmas for DFAs, except it's a bit more annoying, I would say. You just have to do some case analysis, right? You invariably end up with few extra cases to deal with, but that's fine. Okay, so let me write down what this statement is, and the underlying principle is the same, right? We want to say that some function or language cannot be computed by context-free grammars. How do we show this? We're going to identify a property that every context-free language will have, and then show that our function does not have this property. Right? Which is exactly what we did for pumping lemma for DFAs. We said every regular language must have this pumping lemma property, and then there are these languages which do not have this property. Okay. So what is a special property that every context-free grammar should satisfy? Conceptually, it's very similar in that you end up saying, okay, if I have a language which is context-free, and I give you a sufficiently long string, then I can use that string as a base to generate many more strings which should also be in the language. Right? It's like a pumping lemma, right? So you say if something is in the language, then I can repeat the piece and keep on getting strings in the language. Right? It's a very similar form. So let me write the statement first. For every grammar G, there exists a number P such that for all X in the language, the length of X is at least P. X can be broken up as something. Okay? This broken up piece is where it will differ. Okay, you know what? Let me not do that. Let me do it this way. Okay, this is my string X. So when we studied DFAs, we just said, okay, everything which is bigger than the length P can be broken up into three pieces, A, B, C, where the B piece can be repeated as many times as you want. That strong a property is not true for context-free grammars. Right? We already know there are languages which are not regular but can be generated by context-free grammars. Right? So that is not true. Okay, you cannot break it up into three pieces where one piece can be repeated, but I can break it up into five pieces. Okay. So I can break it up into I can write it as, let's say, A, B, C, D, E. Thankfully, we only need five pieces. Okay. And so remember, context-free grammars, they can pair things on either end of a symbol. Right? I can say A goes to 0A0, 0A1, and things like that, right? So this lemma exactly captures these kinds of things, okay? In particular, it will say I can break up X as A, B, C, D, E, such that for every I, if I repeat B and D together, then I'll stay in the language. Does that make sense? So you're not allowed to just say, okay, I repeat B 2 times. That might take you out of the language, but if I take B and D together, I repeat B 2 times, D 2 times, then I should be in the language. It's some kind of paired repetition. Okay, as long as I replicate B and D the same number of times, I can take them out too. That will also be fine. I should be in the language. Okay, so that's the key thing. And the other rules are very similar. The length of B and D put together is non-zero, meaning whatever you're repeating is non-trivial. I'm creating new strings by this repetition. And we also have the final helpful piece, which is that size of BCD is less than or equal to P. Right? So meaning I must have A, B, C, D, E belongs to the language implies A, C, E belongs to the language implies A, B, B, C, D, D, E belongs to the language, and so on. Okay. Any questions about the statement? Let's make sure we understand the statement and then we'll see how to use it. Yeah? Yeah. One of them can be empty, but both of them cannot. Because then when repetition does nothing. Something like that, exactly, right? In fact, the proof really does, we're not going to prove the Pomping lemma for context-free grammars. It's a similar cyclic thing, but you just have to be very careful, a little bit more careful with the trees and make sure that the tree repeats and something like that. Okay? Any other questions about the statement? Okay, very similar flavor. All of the conditions are the same, except we're saying I can always break up any string which is sufficiently big into 5 pieces now, where the second and fourth things, like, they can be repeated in tandem. Okay? All right? All right. Okay, so this is the Pomping lemma. And now let's see how to use it. Okay? So let's use this to show our first surprising thing. As I say, this is surprising because not just that, okay, I found a language which is not context free, but it's a language which is the intersection of two simple things which were context free. Okay? And the proof is going to have the exact same structure as Pomping lemma, right? You'll say, suppose the language is context free, then there is a number P. And now you're playing the same game as Alice and Bob were playing before, right? Alice says this is context free, so Bob says, okay, give me your number P. And then Bob has to propose a challenge string, right? So just as before, the key thing in applying and getting to show things are not context free is to find the right challenge string. Once you do that, most of the rest is basically a case analysis, a little bit more tedious than for DFS. But the key part will always be finding the right challenge string. Okay? So let's suppose L is context free. Then there exists a number P such that Pomping lemma holds. Okay. What challenge string would you pick? Any suggestions? I say the key thing is to pick the right challenge string. In some sense, we don't have that many options, right? Really, the strings in my language are just 0 to the n, 1 to the n, 2 to the n, right? So you only get to choose n, and after that, the structure is completely fixed, right? So what might be a good challenge string to try? Okay, as I said, we need to decide, we don't have too much flexibility here, right? The only thing that we get to decide is how many zeros there are. Okay, let's try the first thing that comes to mind. The whole length of the string must be p. So I'm just going to pick p zeros, p ones, p twos. Okay, so x is 0 to the p, 1 to the p, 2 to the p. Right? And our claim is that this cannot be pumped. Okay, I have a string which is in the language. I always have to, the challenge string must be something in the language, and we want to say I cannot break it up as 5 pieces, sorry, where I can satisfy the pumping lemma. Meaning, just imagine, what was my color code? Yeah. Right, so suppose I have something like this. Oops, I cannot write it there. So this is A, B, C, D, E. Okay, so there's some way of splitting it up such that the pumping lemma holds. That's what Alice claims, and we want to catch her in the lie. So we want to say there is no way of splitting my string x, which is 0 to the p, 1 to the p, 2 to the p, so that you can pump. Okay, and as I said, here things get a little bit tedious. We have to figure out case analysis, right? So what do we know about the pieces? We know, pretty much the only things that we know are the length of BD is greater than 0, and so these are the two conditions that we know. Okay. Now, as I said, we have to do some case analysis. Can you tell me some easy cases? How do I rule out all ways of splitting things? Any suggestions? Yeah? Exactly, right? So in some sense, the punchline is, if you think of this BCD, altogether, the length is at most p, right? So there are essentially two broad cases. One, they sit entirely in one kind of symbol, or they straddle two symbols. Right? Those are the two things that can happen, right? This BCD is of length p, so maybe it's either entirely in the zeros, they're entirely in the ones, they're entirely in the twos, or they can actually go across. But they can only cross one boundary. They cannot cross two boundaries because the middle piece is very big. Okay? So what's happening? So we have cases, either let's say case 1, BCD is only one type of symbol. Okay, so it's maybe content only within. So let's say something, I can have it either here, here, or here. Okay. In this case, I want to say we immediately get a contradiction. Why? Well, if it's only one type of symbol, I pump it, I'm increasing the count of that symbol. If it's only zeros, I do, AB square C D square E, I have more zeros, right? If it's only ones, I end up with more ones. If it's only twos, I end up with more twos. Okay, so case one, but then has an unequal number of different types of symbols. Right, so whatever symbol whatever piece it fell under, its length has increased. So you get a contradiction. Okay. Implies case 2, I have B, C, D straddles a boundary. Okay, so for example, let's say suppose my BCD portion kind of is here. So why is this bad? Any suggestions? Why should this be bad? Like what happens when I pump now? Exactly, right? So you're pumping maybe zeros and ones, but the twos is not changing. All three have to be equal, right? So either this happens or maybe it's on the other boundary. It has ones and twos. But then I will be increasing ones and twos, but not touching zeros. Okay? Either way, I'm increasing 2 and leaving 1 out, right? The one being left out is not increasing, so that's going to give us a violation. Okay? It cannot happen that this thing straddles both boundaries. That's what we are exploiting. Because the middle piece is very big, and the total length of BCD is at most p. Okay? So, but in this case, okay? So either way, by case analysis, we get that AB squared CD squared E is not in the language, a contradiction from pumping limit. Okay? So this implies that overall our language 0 to the n, 1 to the n, 2 to the n is not context free. Okay, any questions? All right, so once you guess the right challenge string, you basically have to do like a case analysis. Usually, you end up with more cases than you would require for DFAs, especially because they can straddle boundaries and so on. Like there's no control on where this repeating piece BCD occurs in the string. I think this was helpful in simplifying the arguments in pumping lemma, right? It only had to occur in the first p symbols. But now this piece BCD, it can kind of move around anywhere. The only thing that we know is that its total length is at most p. Okay, we can exploit that anyway. Okay, any questions about this? Okay, if there are no questions, let's take a short break. When we come back, we will look at double and show that it's also not context free by kind of the same thing. You have to guess the challenge string, do a case analysis, and that will show it. Okay, all right. We want to now show that double is not context free. And the key thing, once again, is to come up with the right challenge string, right? So the setup, I'm going to make the setup, do the easy part, and let you do the hard part, which is suppose double was context free, then there exists a number p such that the conditions of PL hold. Okay, so now we have to come up with the challenge string. So what should the challenge string be? Any guesses? So it's double, remember that. Take some guesses, we'll see if it's correct or not. Yeah.
0, P, 1.
Okay, that does it. So all right. So if I do 0 to the p, 1 to the p, 0 to the p, 1 to the p, okay, kind of maybe makes sense because we want something which is repeating, which has to be in the language, right? And there should be some structure which helps us reason, right? Like BCD is less than or equal to p, then we want to say, okay, either I'm all zeros, all ones, or kind of straddling, and so on and so forth. Okay, so if I were to break it up, what do I get? Okay, so we have p things, p things, p things, p things. Okay, and we are once again trying to say that I can break it up as A, B, C, D, E. Guess my first color was purple. See, this picture is badly not to scale, so let me correct that. It fails in one important aspect. Okay, so someone tells you, okay, I can break it up as A, B, C, D, E, where I have to satisfy the conditions of the pumping lemma. How do I get the contradiction? Any suggestions, guesses? What breaks here? Okay, we once again have two cases, right? So what can happen? Or maybe three cases here, really. Okay, case one, the only thing that we know about BCD is that size of BD is not 0, and together it's of length at most p. Okay. What are the cases? One case is it's completely contained in one block. Okay. So case one, BCD is contained in one block. That's weird. Okay, so maybe it's completely contained in the first block of zeros, maybe in the first block of ones, the second block of zeros, the last block of ones. What happens then? Well, if I repeat it, I end up with either more zeros in the first half or more ones in the first half or in the second half, right? So either way, I'm breaking the symmetry for sure. Okay? So then it's one block. Wow. I don't know what's happening. That is much longer. Okay, which gives us a contradiction, right? And case two is it straddles a boundary. Okay, so for example, hmm, okay, so case two should be what? So let's say case two is BCD straddles a boundary. Okay, and here there are also again two cases. It either straddles like this one, this one, this and this are kind of similar. Right? As I said, usually here you just end up with like more cases than for pumping lemma, but that's what you have to do. Okay. So for example, let's say straddles the 0/1 boundary in the first half. You just have to, really to be fully rigorous, kind of just work through all possible scenarios. Usually there are not that many, or at least, stylistically, there are not that many. Like for example, let's say this is where my BCD is. Okay. Now you end up with the same thing, right? Either B and D are like in zeros and ones, then I pump them. This piece, the first half is becoming unequal to the second half, right? And the same thing, if it's here also, the same stuff happens. Okay. Again, implies all right. Lastly, this one is slightly different. You say first BCD straddles the middle. Okay, so what happens then? Well, whichever I pump, I'll either end up with more ones here. When I pump it, either I'll increase the number of ones or the number of zeros in here without changing the two borders, right? So that's the case analysis. And if B is not empty, then I'm increasing the number of ones, but the number of ones here is not changing. If D is not empty, then I'm increasing the number of zeros, but the number of zeros at the beginning is not changing. Make sense? Okay. So it's just a matter of making sure that you cover all possible cases. Implies either the number of ones or the number of zeros won't match. Okay. So for example, if you have to do something like this, you need to just make sure that you hit all of the cases, even if the arguments are very similar. Make sure that you hit all of the cases. Any questions about this? Yeah.
Do we need three cases, or can we just have like this last case and then just the case that it's in one half?
You can. Yeah. In fact, I should have written 4 cases is the first boundary or the third boundary and so on. But you can definitely, like as I said, let's say straddles in the first half, right, or the second half. Yeah, yeah, you can definitely do what you suggested as well. That would also have been enough. Okay. Yeah, so there'll be a few cases. Just make sure that you hit all of them and you're not cutting corners. Because sometimes the devil might be in the details. You can figure out why certain language. If you cut some corners, you'll end up with some context-free grammars which are not context-free. So you have to be careful. Okay. Any other questions about pumping lemma for CFGs and what we learned importantly from this, which is that basic closure properties fail for CFGs. Yeah. Yes, right, because then you can pump them, right? So for instance, if BCD can span two boundaries, what can happen is, let's say my B is here and D is here. Okay. Now, when I increase the number of one, pump both of them together, I'm always in the language, right? Because I'm increasing ones, all of those will be in the language. So we are really exploiting the fact that I cannot have B sitting here, D sitting here, and C is entirely in here. Because the length of BCD is at most B. Okay? So we are exploiting that crucially. Okay? Any other questions? All right. So we learned a lot about context-free grammars. Now, let us reason about some meta properties of context-free grammars, right? And there are two important questions. One we will answer. The other one is a very important question, and but the answer is a little bit tedious. I'll just state it. And in some previous years I covered it, but it's a bunch of cases that I don't really like, so I'm not going to do it. Okay. All right. So the first thing is the following. Just as we defined semantic properties for Turing machines, I'm going to talk about, why is this happening? Okay, let's see. Someone getting some random lines. Okay, semantic properties of CFGs. So let's say I have a function that takes a grammar G as input. Okay, so whatever its input is, we think of it as the encoding of a grammar, right? Just as we did encoding of Turing machine, circuits, and everything, we can also encode grammars as bit strings. Okay, so I'm encoding a grammar as input, and as input is semantic. Just as for Turing machines, if for all grammars G comma G prime that are equivalent, f of G equals f of G prime. Okay, so equivalent meaning the language generated by grammar G is the same as the language generated by grammar G prime. Okay, it doesn't depend on, basically f of G doesn't really depend on what are the variable names, how you wrote down the rules, but actually depends only on what language you are generating. Okay, I might change some variable names, it shouldn't change the value of capital F. You might add some spurious rules, it shouldn't change what you get. Okay, for example, we already saw two seemingly different rules which were generating the same language. So f should give you the same value on both of those grammars. Okay, right? So for Turing machines, every non-trivial semantic property was super hard. You cannot compute it, right? Fortunately, there are semantic properties of context-free grammars that we can actually compute. But as I said, Turing machines are great, but it gives you this strong limitation that you cannot reason about Turing machines. No semantic property, other than the most trivial ones, are computable. Whereas once I restrict the model of computation, kind of change how you can do the computation, then I can start reasoning about them, at least in some cases. Okay? So that's the model. Somehow I restrict the model, and now maybe there are some semantic properties which I can actually compute. So I can start reasoning about programs somewhat efficiently now. Right? And the example that we'll look at for that is actually an important one. And it's something that we already saw for Turing machines. Remember, we defined not empty of a Turing machine, right? So not empty took the description of a Turing machine and checked if there is a single string which makes M output 1. Right? And the same thing here. So not empty CFG takes the description of a grammar, right? And outputs 1 if there exists some string x and g, 0 otherwise. Okay, so this is the same as saying there exists some x such that the function computed by the grammar is 1 and is 0 otherwise. Okay, That is the grammar trivial or is it doing something interesting? Okay. I mean, for example, I can have some silly set of rules like this. S goes to AB, B goes to CD, A goes to 1, C goes to 0. But this never generates a string. The language of this grammar is completely empty. Why? Why do you think so? Why is the grammar empty here? The reason is no matter what you do, I go to A, B, B goes to CD, I cannot get rid of D. Right? D is a variable. So for something to be in the language, it should contain only terminals. But I'm always left over with D, and I'm not getting rid of it. So the language is empty. Okay? And the cool thing is, unlike for Turing machines, not empty CFG is actually computable. There is an efficient algorithm which can check if the language generated by grammar is empty. I cannot do this for Turing machines, but I can do this for context-free grammars. Okay, if you make it context sensitive, then again things might break, but for context-free grammars, we can do it. Okay, and how am I going to show that it is computable? I want to say it is computable, meaning there is a Turing machine which can compute not empty CFG. So what's the first thing that you would do if I ask you to show something is computable? Aren't you hungry? Yeah. Write a high-level program. So we're going to have our cake. Okay. So suppose someone gave you the rules of a grammar. How would you kind of come up with let's say Python program to check if the rules of the grammar generate a meaningful string? Yeah.
Only add that part and by the end.
Almost, but the point is you might keep on adding and deleting, right? Like for example, here I might keep going A to B, B to CD, right? But what if this was something like B to BD? Right, I'll keep adding B, deleting B, adding B, deleting B. So somehow I'm not making progress there. Maybe, but I think there's a simpler way. Yeah, that's too complicated. That's like solving that's full programming language stuff, right? We at least don't need to do that for this. That will definitely do it, but it's a bit too complicated for this. Okay, but I think what you were suggesting earlier is kind of the right track. So somehow all we need to do is to make sure that we can get rid of all variables. In some rules, some way of derivation, I can get rid of all variables. I don't care how long it is, or if I didn't do it the most efficient way. That's also fine. I just need to check if there is some way of getting rid of all of the variables. Okay. So think of it as some kind of like, DFS, breadth first search kind of problem. Starting from the end. Any suggestions? Yeah. Mm, apply each rule only once. You might still end up in trouble, I think. Let's see. So that's a good suggestion. So, but what order? Okay. Any order, and you're saying, just find all possible ways, all possible orderings of the rules. Okay. Let's say I think we decide. Let's say try all possible orderings of the rules where no rule is repeated. Okay. And see check if one of these leads to a terminal. Yeah, I think this would work. Yeah, I think this would work. There's also a more efficient way though. If there are k rules, this is like k factorial at the very least. Right? I need to find all possible orderings. So this is a bit more expensive than what maybe, let's say, you would do if you're actually trying to program it. Yeah? Exactly, right? Some kind of dynamic programming kind of thing. You start with all terminals as good. If a rule only goes to terminal, if a variable only goes to terminals, now that's also good. Okay, and then I can keep on enlarging the good set until the start becomes good, or I do not mark any new variables as good. Okay, so this also works, but I think it's a little bit more expensive than what maybe you would do on an actual computer. So let's do that. Yeah, so the idea one is this. Idea two is the following. Start by calling all terminals as good. Okay. And I just have a bunch of good things. Either terminals or variables. I just have a bunch of good uh, uh, variables slash terminals, right? And if a variable has a rule where the right hand side only has good elements, mark the variable as good. Okay, so if there is a to 0, 1, then I'm going to mark a as good. And if there is a rule which says b goes to a, I'm also going to mark b as good in the next round. Okay, and eventually, if start s is marked good, then the language is not empty. Okay, some kind of infection process. Let's say you infect all of the terminals. If there is a variable which is only connected to infected ones, I mark that as infected and then kind of keep propagating until I stop seeing any changes. At that point, I check if the start variable is good. If it is good, the language is not empty. Okay, so let me write that down. while any changes are made. Go through every rule. If a variable A has a rule to only good things on the right, mark A as good. Okay, so every time you go through all of the rules and then you mark something as good, if there is a chance, and then you keep proceeding. Okay, so the runtime of this will basically be the number of rules times the number of variables in the worst case. So it's definitely something that you can run reasonably well. Okay, and then if start is good, LG is not empty. Okay, makes sense? Any questions about this? So do this for every rule, I should say. Okay. Okay. So this tells you that there are some non-trivial properties that you can actually compute. Non-trivial semantic properties. Maybe let me write it like this. Okay. Now, this is some progress, but even for context-free grammars, not all semantic properties are computable. Okay. All we just showed is kind of for Turing machines, you had the opposite dichotomy, right? Every non-trivial semantic property is uncomputable. Here, some semantic properties are computable, that's what we saw. But at the same time, there are some other semantic properties which are actually uncomputable. Okay. But showing this is way more complicated. We're not going to do that. Okay, but I'm just going to state it. So is full. Again, this is sort of a bizarre closure property of context-free grammars. Failure of closure properties. So is full CFG is a function which takes the description of a context-free grammar as input. Okay, and outputs 1 if the language of the grammar is everything. Not empty, checked if the language was empty. Is full is checking if you end up generating every possible string. Both seem very trivial, right? You're just checking if the language is somehow trivial. In that case, you're checking if the language is the empty set. Here, you're checking if the language is every possible string. Okay? Right? But the bizarre thing, really bizarre to me, when I first learned it, I didn't believe it, is that not empty is computable. Okay? And theorem is full CFG is uncomputable. We are not going to prove this. Okay. This is also a semantic property. It only depends on what the language is. It doesn't depend on what the rules are, what variable names you use, etc. But nevertheless, this bizarrely turns out to be uncomputable. It's quite a complicated reduction. You have to somehow embed halting problem in here, and it's kind of crazy. Okay. Yes.
This doesn't depend on rules, but doesn't it depend on
It depends on the language generated by the grammar, right? So, but it's semantic, right? Meaning if I have two grammars which are equivalent, then is full would be either 1 or 0 on both of them, right? So it really depends on the semantic properties of the grammar, what you're generating rather than, like, let's say I take G, I change the variable names. Is full of G is not going to change. Yeah?
Because to check is full, you have to like to verify that you have to actually check like every single step.
Not quite, right? You could have kind of made the same argument for not empty too, right? You could have said, okay, to check not empty, I need to make sure that there is no string that is in the language, right? But somehow we got around that, okay? And this also, think about it afterward. This is uncomputable also shows indirectly that context-free grammars are not closed under complement. Okay, if they were closed under complement, you would get a contradiction to this too. But there's something to think about afterward. Because if suppose for every grammar, the complement of it is also a context-free grammar, then if LG is sigma star, the complement of that is empty. If that was also a context-free grammar, then it would be not empty, so you would compute it. So the failure of closure properties is kind of implicitly showing up again here. Okay, but this is a highly surprising statement. And similarly, there are lots of other properties, like if I give you two grammars and ask you to check if they're computing the same thing, uncomputable. Okay, but some things are computable even with this restricted power. We haven't fixed all uncomputability issues, but we fixed some of them. All right. So this is all we will cover about context-free grammars. The next 4 lectures, we're going to delve into a completely different world, which is quantum circuits. Okay. So if you're rough on the edges of linear algebra, I recommend revising some of this stuff. What do you need to revise? Basically simple, like let's say, what are 2-dimensional vectors? What are 3-dimensional vectors? What are 2x2 matrices, 3x3 matrices? How do I multiply 2x2 matrices? How do I multiply 3x3 matrices? Okay, just check up on these things. I think that will make it easier. I'm sure most of you have seen this, are comfortable with it, but just review them in any case. And then, we'll talk about if this is bizarre, what comes next is way more bizarre. It's a quantum leap, right? Okay, I'll see you all on Monday.